touch a metal doorknob after walking across a carpet and you feel a sharp snap on your fingertip. That snap is electricity. Charge built up on your body as you walked, transferred to the doorknob the moment you got close enough, and released in an instant. No batteries, no wires, just movement, build-up, and sudden release. The force behind that snap is the same force that makes a balloon stick to a wall after you rub it, that makes freshly dried laundry cling to itself, that makes hair follow a comb on a dry day. That snap is an electrical discharge caused by a build-up of electric charge and the electric field it creates. That is electricity. Now think about a magnet. The pull is steady and silent. It requires no friction, no movement, no build-up of any kind. A magnet simply sits there and pulls certain things toward it. Iron filings, other magnets, a refrigerator door. It is a permanent, invisible reach that certain materials have and most do not. That is magnetism. These two things feel nothing like each other. One is about charge, friction, and sudden release. The other is a quiet, permanent pull belonging to certain metals. They affect different materials, arise from different causes, and behave differently when observed carefully. Electric forces pull directly toward or push directly away, straight along the line between the charged object and whatever it acts on. Magnetic forces deflect things sideways. A compass needle rotates and aligns rather than getting dragged straight in. Different geometry, different materials, different causes. For centuries, that difference was taken at face value. Electricity was one subject. Magnetism was another. The two sat in separate corners of natural philosophy, studied independently, described by separate frameworks, with nothing pointing toward a shared origin. That picture held until a single observation broke it. A Danish physicist, mid-lecture, brought a wire carrying electrical current near a compass needle and watched it swing. Electricity reached across the assumed boundary and moved something magnetic. The separation that had felt obvious and structural turned out to be a surface appearance. Once that boundary cracked, the question became how deep the connection actually ran. The answer took decades to trace, and where it led was somewhere nobody anticipated. The connection between electricity and magnetism, followed to its end, produced something that neither force seemed to contain on its own. Something that moves through empty space, sustained by nothing but the fields themselves, traveling at a precise speed that could be calculated from electrical and magnetic measurements alone. Something that had been measured, named and studied for centuries before anyone understood what it actually was. How does current in a wire move a compass needle? What happens when you look for the connection running in the opposite direction? And what emerges when the two forces are finally understood as one? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, let me know in the comments. I always wonder which curiosities other people carry around with them. With that said, let's get back to the topic. The descent begins with electricity standing alone. What charge is, what it does to the space around it, and what force it produces before magnetism enters the picture at all. Everything around you is made of atoms, and every atom contains charge. The nucleus at the center carries positive charge, held there by protons. The electrons surrounding it carry negative charge, orbiting in the layered structure that the previous episode on quantum mechanics described in detail. In an ordinary, undisturbed atom, those two amounts balance exactly. The atom as a whole is neutral. It neither pulls nor pushes on other atoms through electrical force, because its positive and negative charges cancel each other out completely. leaving nothing for the electric force to act on from the outside. That balance is the default state of matter. It is why most objects in everyday life do not visibly attract or repel each other. The charge is there, enormous amounts of it, but it is paired and cancelled at every point. What electricity requires is an imbalance. When charge is separated, when electrons are stripped away from one surface and deposited onto another, the cancellation breaks. The surface that lost electrons now has more positive charge than negative. The surface that gained them has more negative than positive. Both surfaces now have something the electric force can act on, and the force acts immediately. The character of that force was described precisely by Charles-Augustin de Coulomb in the late 18th century. Two charged objects attract each other if their charges are opposite, and repel each other if their charges are the same. The strength of the force depends on two things: the size of the charges involved and the distance between them. Double the charge and the force doubles. Double the distance and the force drops to a quarter of its previous value. That relationship between force and distance is the same mathematical shape as gravity. Both weaken with the square of the distance, but the electric force is incomparably stronger. Between two electrons, the electric repulsion is roughly 42 orders of magnitude larger than the gravitational attraction. Gravity wins at cosmic scales only because matter is electrically neutral in bulk. At the scale of particles, electricity dominates completely. What Coulomb's description captured was the force between charges treated as points. The force along the line connecting them, pulling or pushing depending on their signs. That picture is accurate and useful, but it carries a hidden assumption that becomes important later. It treats the force as acting directly between the two charges, reaching across the empty space between them instantaneously. That assumption of direct action at a distance worked well enough for calculating forces between static charges, but it left a question open that nobody had a satisfying answer to yet. How does one charge know the other is there? What carries the influence across the gap? That question has an answer, and the answer changes everything about how electricity is understood. But reaching it requires one more step first: understanding what a charge does to the space around it, before any second charge arrives to feel the effect. Somewhere in the ancient world, people noticed that certain stones found in a region of Asia Minor called Magnesia would pull iron toward them without being touched. The stones required no rubbing, no preparation, no input of any kind. They simply sat there and reached. That reaching was magnetic force, and for a long time it remained one of the more mysterious things in natural philosophy. A force with no obvious cause, acting on specific materials and ignoring everything else, obeying no rule that anyone could clearly articulate. The practical consequences arrived before the theoretical understanding. By the 11th century, navigators had discovered that a sliver of magnetized iron, suspended freely, would rotate until it pointed in a fixed direction, toward the north. The compass followed from that observation, and with the compass came centuries of navigation, exploration, and trade. Magnetism was enormously useful long before anyone understood what produced it. The phenomenon was real, reliable, and completely unexplained. What careful observation established over time was a set of consistent behaviors. Every magnet has two poles, regions where the magnetic pull is strongest, and those poles always come in pairs. Bring two magnets together with opposite poles facing, and they pull toward each other. Flip one around so matching poles face and they push apart. Cut a magnet in half expecting to isolate a single pole, and the result is two smaller magnets, each with its own pair of poles. The poles cannot be separated. Unlike electric charge, which can be isolated as purely positive or purely negative, magnetic poles always appear together. A north pole without a south pole has never been found in any experiment ever conducted. The force a magnet exerts also has a distinctive geometry. It does not pull things directly inward along a straight line the way a charged object pulls opposite charges toward it. It curves. Iron filings scattered around a magnet arrange themselves into arcing lines that loop from one pole to the other, tracing a shape that fills the space around the magnet in all directions. That pattern was not merely decorative. It was a record of something existing in the space around the magnet, a region where the magnetic force could be felt by anything sensitive to it, extending outward from the magnet in a structured, mappable way. For centuries that structured reach remained a curiosity. Magnetism acted on iron and on other magnets. It left everything else untouched. Charged objects, rubbed amber, crackling wool. None of these produced any effect on a compass needle. The two forces observed their boundary faithfully, and nothing in the behavior of either one suggested that this boundary would ever break. What broke it was something that nobody thought to look for, because the thing that broke it did not exist until humans learned to move charge deliberately through a wire. In 1820, a Danish physicist named Hans Christian Oersted was preparing a lecture demonstration when he noticed something that had no business happening. He had a wire carrying electrical current running across his bench, and nearby sat a compass. When the current flowed, the compass needle moved. When the current stopped, the needle returned to its resting position. The effect was repeatable, immediate, and completely outside anything the existing framework could account for. Electricity had just reached across the assumed boundary and touched magnetism directly. Oersted had not set out to find a connection. He was demonstrating something else entirely. The observation arrived uninvited, and its implications took time to absorb. What the deflecting compass needle said, in the plainest physical terms, was that a wire carrying current produced something in the space around it that acted on a magnetic object. That something was a magnetic field, generated not by a lodestone, not by a piece of magnetized iron, but by moving electrical charge. The cause of the magnetic effect was electricity in motion. The geometry of what Oersted observed made the result even harder to fit into existing intuitions. The compass needle did not point toward the wire or away from it the way it would if the wire were simply attracting or repelling it. The needle oriented itself at a right angle to the wire, circling around it. When Oersted moved the compass to different positions around the wire, the needle always aligned tangentially, tracing a circular path centered on the wire. The magnetic field produced by the current did not radiate outward like the electric field of a charged object. It wrapped around the wire in closed loops, a geometry that had no precedent in anything electricity had produced before. This was more than a curiosity. It was a structural rupture in the classification of natural forces. Two phenomena that had been treated as entirely separate for centuries turned out to share a productive relationship. Moving charge, current, generated magnetism. The question that followed immediately was whether the relationship ran in only one direction, or whether magnetism could, under the right conditions, reach back and produce something electrical in return. That question would take another decade to answer, and the person who answered it approached it not from mathematics, but from a physical intuition about the space surrounding magnets that was unlike anything his contemporaries were thinking. News of Oersted's observations spread quickly through the scientific community of Europe, and within weeks a French physicist named André-Marie Ampere had begun turning the observation into something precise and quantitative. Where Oersted had noticed the effect, Ampere measured it. Where Oersted had described the deflection qualitatively, Ampere worked out the exact relationship between the current in a wire and the magnetic field it produced in the space around it. What Ampere established through careful experiment was that the magnetic field surrounding a current-carrying wire had a strength that depended on two things: how much current was flowing and how far from the wire you were measuring. More current meant a stronger field. Greater distance meant a weaker one. The relationship with distance followed a clean mathematical rule. The field weakened in direct proportion to the distance from the wire, falling to half its value when the distance doubled. That precise dependence was not assumed. It was measured repeatedly with instruments sensitive enough to confirm it. The geometry Oersted had noticed, the field circling around the wire rather than radiating outward from it, was built into Ampere's description from the start. The magnetic field did not point away from the wire like the spokes of a wheel. It wrapped around it in closed loops, like rings stacked along the wire's length, each ring centered on the wire and lying in a plane perpendicular to it. The direction of those loops depended on the direction of the current. Reverse the current, and the loops reversed with it, the compass needle swinging to the opposite side. The field was not a passive presence. It had a handedness, a directionality tied precisely to the motion of the charge producing it. Ampere went further. He showed that two parallel wires carrying current exerted forces on each other, not because either wire was electrically charged in the ordinary sense, but because each wire sat inside the magnetic field produced by the other. Two currents flowing in the same direction pulled the wires together. Two currents flowing in opposite directions pushed them apart. The force between wires carrying current was a magnetic force, produced entirely by moving charge, with no static charge involved at all. Electricity in motion was generating magnetism, and that magnetism was generating mechanical force on other moving charges nearby. What Ampere's work made precise was the one-way description of the link Oersted had cracked open. Moving charge produces a magnetic field. The field wraps around the current in closed loops. Its strength and direction are exactly calculable from the current that produces it. That half of the connection was now quantified and dependable, but the other half, whether a magnetic field could reach back and produce something electrical, remained untested. The person who would test it was already thinking about the problem, and he was approaching it from a direction that had nothing to do with currents or wires. Michael Faraday had almost no formal mathematical training. He had taught himself natural philosophy from books while working as a bookbinder's apprentice, and what he brought to the study of electromagnetism was not algebraic fluency, but an extraordinary physical intuition about the behavior of invisible forces in space. Where Ampere thought in equations, Faraday thought in pictures, and the picture he carried in his mind of magnetic force spreading outward from a magnet in structured lines that filled the surrounding space led him to a question that his more mathematically inclined contemporaries had not thought to ask in quite the same way. Ampere had shown that a steady current produced a steady magnetic field. Faraday turned the relationship around and asked whether a magnetic field could produce a current. He wound two coils of wire around the same iron ring, connected one coil to a battery and the other to a sensitive current detector, and watched what happened when he switched the battery on. For a brief moment, the detector registered a current in the second coil, a coil that had no battery connected to it, no direct electrical connection to the first, nothing driving charge through it except whatever the magnetic field was doing. Then the current vanished. The detector returned to zero and stayed there, even while the battery continued pushing current through the first coil, and the magnetic field continued existing inside the iron ring. That result carried a precise and surprising message. A steady magnetic field produced no current in a nearby conductor, but a changing magnetic field, The field, surging from zero to its full strength in the moment the battery was switched on, produced a current for exactly as long as the change was happening. Faraday checked the other end of the process. When he switched the battery off and the magnetic field collapsed back to zero, the detector registered a current again, briefly in the opposite direction. The current appeared during the change, disappeared when the change stopped, and reversed when the change ran the other way. What Faraday had found was that the relevant quantity was not the magnetic field itself, but its rate of change. A magnetic field sitting still produced nothing electrical. A magnetic field growing or shrinking produced an electrical effect in any conductor nearby, and the size of that effect was tied to how rapidly the field was changing. He tested this in a different way, without any battery at all. He pushed a permanent magnet into a coil of wire and watched the detector swing. He pulled it back out and watched it swing the other way. The motion of the magnet, the fact that the field threading through the coil was changing as the magnet moved, was sufficient to drive a current. No battery, no chemical reaction, just a changing magnetic field, and charge began to move. This was the return link that completed the first loop of the connection. Moving charge produced a magnetic field. A changing magnetic field produced a moving charge. The relationship ran in both directions, and the universe had been quietly demonstrating both halves of it all along. What remained was to understand not just that the link existed, but what was physically happening in the space between, what was actually carrying the influence from the changing magnet to the wire, sitting some distance away from it. Faraday's experiments had established that a changing magnetic field could drive current through a wire sitting at a distance from the source of that change. But the result raised a question that the experimental description alone could not answer. How did the wire know the magnetic field was changing? What crossed the gap between the magnet and the conductor? In the framework inherited from Newton, forces acted between objects directly. One body reached across empty space and pulled or pushed another. That framework had worked well enough for gravity and for static electric forces, but Faraday found it deeply unsatisfying, and the picture he developed to replace it turned out to be one of the most consequential ideas in the history of physics. Faraday proposed that the space around a magnet or a charged object was not empty. It was modified. Something existed there, filling the region in all directions, structured and mappable, present at every point whether or not any second object was there to feel it. He called the lines tracing that structure field lines, and he thought of them as physically real, not mathematical conveniences, not bookkeeping tools for calculating forces, but actual features of the space itself. The field was not a property of the magnet. It was something the magnet produced in the surrounding space, something that existed independently of the magnet once created, something that could change and evolve on its own terms. This shift in perspective was more radical than it might initially appear. In the action at a distance picture, the force between two charges was a relationship between two objects. Remove one object, and the concept of force lost its meaning. In Faraday's picture, the field existed at every point in space, regardless of whether a second charge was present to feel it. A charge modified the space around it, and that modification was the field. A second charge, placed anywhere in that modified space, felt a force because it was sitting inside the field, not because the first charge was reaching across the gap to act on it directly. The field lines Faraday drew were not arbitrary. They had a direction at every point, indicating which way a small positive charge would be pushed if placed there. They had a density, with lines packed more closely together where the field was stronger and spreading apart where it was weaker. The closed loop surrounding a current-carrying wire that Ampere had described were field lines of exactly this kind, not abstractions but records of how the space around the wire had been physically altered by the moving charge inside it. What made this picture powerful beyond its visual clarity was what it implied about how changes propagate. In the action at a distance picture, when a charge moved, every other charge in the universe felt the change instantaneously, regardless of distance. In the field picture, a moving charge first altered the field immediately around it. That alteration then spread outward through the field, reaching distant points only after some travel time. The field was not just a static map of forces, it was a dynamic medium, capable of carrying disturbances from one place to another. How fast those disturbances travelled and what governed their propagation was a question the field picture made possible to ask in a way the old framework never had. Answering it required someone to take Faraday's physical intuition and press it into precise mathematical form, and that was the task that fell to James Clerk Maxwell. Faraday's field was not merely a way of visualizing forces, it was a physical entity occupying space, and physical entities that occupy space carry energy. This was not immediately obvious, and for many of Faraday's contemporaries it was not immediately accepted. The idea that empty space between two magnets or two charged objects contained something real, something with measurable energy stored in it, required a significant adjustment to what physics considered a legitimate ingredient of the world. But the mathematics forced the conclusion, and once accepted, it changed what the field actually was in a deep and permanent way. Consider two opposite electric charges held apart at a fixed distance. Bringing them together releases energy. You can feel it if you hold two oppositely charged objects and let them snap together. That energy had to come from somewhere. In the action at a distance picture, it lived in the configuration of the two charges, in their spatial relationship to each other. In the field picture, it lived in the field itself, distributed throughout the space between and around the charges. The field in the region between them was stronger than the field far away, and the energy was densest where the field was strongest. Move the charges together, and the field configuration changed, the stored energy decreased, and that decrease appeared as the kinetic energy of the charges snapping toward each other. The same logic applied to magnetic fields. A current flowing through a wire produced a magnetic field in the space around it. Establishing that field required energy drawn from whatever was driving the current. Switch the current off and the field collapsed, and as it collapsed, it drove a brief surge of current back through the wire, returning the stored energy to the circuit. The energy had been sitting in the magnetic field, in the space around the wire, waiting. The field was not a passive description of forces that would act if something were placed there. It was an active store of energy, present and real regardless of whether anything was there to feel it. This had a precise mathematical expression. The energy stored in an electric field at any point in space depended on the strength of the field at that point. The energy stored in a magnetic field depended similarly on the magnetic field strength there. Summing those contributions across all of space gave the total energy held in the fields surrounding any configuration of charges and currents. That total was exactly equal to the energy that would be released if the configuration were allowed to relax. The charges flying together, the currents dying away, the fields collapsing back to zero. What this established was that the field was not a mathematical shorthand for something that really lived in the charges themselves. The energy was genuinely out there, in the space between things, stored in the structure of the field at every point. A region of space threaded by a strong magnetic field contained more energy than the same region with no field, in the same way that a compressed spring contains more energy than a relaxed one. The field was as real as the spring, and a field that carried energy could, in principle, transport that energy from one place to another if the field itself changed and those changes propagated through space. That possibility, energy moving through space carried by a changing field, was about to become the central question. By the time James Clerk Maxwell turned his attention to electricity and magnetism in the 1850s, the experimental picture had two firmly established results sitting side by side. Oersted and Ampere had shown that moving charge, current, produced a magnetic field in the space around it. Faraday had shown that a changing magnetic field produced an electric field in any conductor nearby. The two forces were linked in both directions, each capable of generating the other under the right conditions. What Maxwell set out to do was take Faraday's physical intuition about fields and press it into a single coherent mathematical framework that captured everything known about both forces simultaneously. As he worked through the mathematics, something began to trouble him. Ampere's description of how currents produced magnetic fields was precise and experimentally confirmed for every situation anyone had tested it in. But when Maxwell examined the equation carefully, he found that it contained a hidden assumption, one that held perfectly well for steady currents flowing continuously through unbroken wires, but broke down in a specific situation that Ampere had never needed to consider. The situation involved a capacitor. A capacitor is simply two conducting plates placed close together, but not touching, with a gap of empty space between them. Connect a capacitor to a battery and charge begins to build up on the plates. Positive charge accumulating on one plate, negative on the other. While that charging is happening, current flows through the wires leading to the plates. That current produces a magnetic field around the wires, exactly as Ampere's law described. But in the gap between the plates, no current flows at all. No charge crosses the gap. The space there is empty of moving charge. This created a precise and uncomfortable inconsistency. Ampere's law said that magnetic fields were produced by currents. In the wires leading to the capacitor, there was current and there was a magnetic field. In the gap between the plates, there was no current, and yet the magnetic field could not simply stop at the edge of the gap and vanish. The field had to behave continuously, a magnetic field that existed on one side of an imaginary surface drawn through the gap had to connect smoothly to the field on the other side. Ampere's law, applied strictly, gave contradictory results depending on which surface you chose to apply it to. The mathematics was inconsistent, and Maxwell knew that an inconsistent equation could not be a complete description of nature. Something was missing. Something was happening in the gap between the capacitor plates that Ampere's law had no term to account for, and identifying what that something was would require Maxwell to look not at the current that was absent from the gap, but at something that was very much present there and changing. While no charge crossed the gap between the capacitor plates, something else was happening there that Maxwell recognized as physically significant. As charge built up on the plates, the electric field in the gap was growing. Positive charge accumulating on one plate and negative charge on the other produced an electric field pointing across the gap from one plate to the other, and that field was not static. It was increasing steadily as long as the charging process continued. The gap contained no current, but it contained a changing electric field, and Maxwell made a proposal that was bold precisely because it had no direct experimental confirmation at the time he made it. He proposed that a changing electric field produced a magnetic field in exactly the same way that a current did. The two were not the same thing physically. A current was moving charge. A changing electric field involved no moving charge at all. But mathematically, Maxwell showed that adding a term to Ampere's law Representing the changing electric field restored the consistency that the capacitor problem had broken. With that term included, the magnetic field no longer depended on which imaginary surface you chose to evaluate it across. The answer came out the same regardless, which is what a consistent physical law requires. Maxwell called this additional term the displacement current, a name that has caused confusion ever since because it is not a current in the ordinary sense of moving charge. It is the magnetic effect produced by a changing electric field in a region of space, including empty space where no charge is present at all. In the gap between the capacitor plates, the growing electric field was generating a magnetic field around it, smoothly continuing the magnetic effect of the current in the wires on either side of the gap. The field in the gap was doing what the current in the wires was doing, not by moving charge, but by changing. The significance of this addition reached far beyond fixing an inconsistency in one equation. What Maxwell had established by symmetry was a complete and closed relationship between electric and magnetic fields. Faraday had shown that a changing magnetic field produced an electric field. Maxwell had now shown that a changing electric field produced a magnetic field. Each force generated the other whenever it changed. The relationship no longer required any charge or any current to sustain it. Two fields, each changing, each generating the other, could in principle exist and evolve in empty space with no material source driving them at all. That possibility was not yet a conclusion. It was a consequence waiting to be drawn out of the completed mathematics. Maxwell had closed the symmetry. What the closed symmetry implied about the behavior of fields in empty space was the next question, and answering it required writing all four governing equations down together and asking what they permitted. Maxwell now had everything he needed. Faraday's result, Ampere's law corrected with a displacement current term, and two additional relationships describing how electric and magnetic fields behaved in space. He assembled these into a set of four equations that together formed a complete description of everything electricity and magnetism could do. Four equations covering all of it: the production of electric fields by charges, the absence of isolated magnetic poles, the production of magnetic fields by currents and by changing electric fields, the production of electric fields by changing magnetic fields. Every experimental result accumulated over the previous century fit inside this framework without exception. The first equation described how electric fields spread outward from charges. A positive charge pushed the electric field outward in all directions around it. A negative charge pulled it inward. The strength of the field at any distance from the charge followed the same inverse square relationship that Coulomb had measured. That result, which had been established experimentally decades earlier, fell out of the first equation as a direct consequence rather than a separate assumption. The second equation stated something about magnetic fields that every experiment had confirmed, but that still carried a deep implication. Magnetic field lines always formed closed loops. They had no beginning and no end. There were no isolated magnetic charges in nature, no magnetic equivalent of a single positive or negative electric charge sitting alone. Every field line that left a north pole returned to a south pole. The second equation captured that fact in a single mathematical statement. The third equation was Faraday's result in mathematical form. A changing magnetic field produced an electric field curling around it. The faster the magnetic field changed, the stronger the electric field it generated. The direction of that electric field was tied precisely to the direction of the magnetic change, following a relationship that experiments had confirmed across every configuration Faraday and his successors had tested. The fourth equation was Ampere's law with Maxwell's displacement current included. A current produced a magnetic field wrapping around it. A changing electric field produced the same kind of magnetic field, even in regions where no current flowed. The correction Maxwell had introduced to resolve the capacitor inconsistency was now a permanent and load-bearing part of the framework. What made these four equations extraordinary was not any single one of them. It was what they implied in combination. Each equation on its own described something already known from experiment. Together, they formed a closed and self-consistent system, describing how electric and magnetic fields influenced each other and evolved through space and time. And a closed, self-consistent system of equations can be interrogated mathematically for solutions that the experiments leading to it never directly revealed. Maxwell interrogated his equations, and what he found waiting inside them was something nobody had put there. A set of equations describing how physical quantities change in space and time can be searched for a particular kind of solution, one where the quantities oscillate, rising and falling in a repeating pattern that moves through space as it evolves. This is a wave solution, and finding one inside a set of equations means the physical system those equations describe is capable of supporting a wave. Maxwell searched his four equations for exactly this kind of solution, and he found one. The process required combining the equations in a specific way. Faraday's equation said that a changing magnetic field produced a curling electric field. Maxwell's corrected Ampere equation said that a changing electric field produced a curling magnetic field. Pressing these two results together mathematically produced something that physicists recognize immediately as a wave equation, a precise mathematical structure describing a disturbance that propagates through space at a definite speed, sustaining itself as it travels. The wave that emerged from this process had a specific character. It consisted of an electric field and a magnetic field oscillating together, each one perpendicular to the other, and both perpendicular to the direction the wave was traveling. The electric field rose to a peak, fell back through zero, dropped to a trough, and returned to zero, cycling continuously. The magnetic field did the same, locked in step with the electric field, each one driving the other forward. The changing electric field continuously regenerated the magnetic field beside it. The changing magnetic field continuously regenerated the electric field beside it. The two fields sustained each other through empty space with no charge, no current, and no material medium required to carry them. This was something genuinely new. Everything in the experimental record up to that point involved fields attached in some way to their sources. Electric fields spread outward from charges. Magnetic fields wrapped around currents. The fields existed because the sources existed, and removing the sources removed the fields. What Maxwell's wave solution described was a field structure that had detached from its source entirely, carrying itself forward through empty space by the mutual regeneration of its two components. Once launched, it required nothing from the outside to continue. The changing electric field produced the magnetic field one step ahead. The changing magnetic field produced the electric field one step further. The wave was self-propelling, moving through space, as a consequence of nothing more than the relationship between the two fields that Maxwell's equations described. The existence of such a wave followed necessarily from the mathematics. Maxwell had not assumed it or constructed it by hand. He had found it waiting inside the equations as an inevitable consequence of the symmetry between electricity and magnetism that his displacement current term had completed. The wave was there because the symmetry demanded it. What remained was to calculate how fast it travelled, and that calculation produced a number that stopped Maxwell in his tracks. The wave equation Maxwell extracted from his four equations did not just describe the shape of the oscillating fields. It contained a precise expression for the speed at which the wave propagated through empty space. That speed was not a free parameter that could take any value depending on conditions. It was fixed, determined entirely by two quantities that had been measured in laboratories through experiments that had nothing to do with waves or propagation or anything moving at all. The first quantity described how strongly electric fields responded to charges in empty space. It had been measured carefully through experiments with capacitors and static charge distributions, establishing precisely how much electric field a given amount of charge produced in a vacuum. The second quantity described the same relationship for magnetic fields, measuring how strongly a given current produced a magnetic field in empty space. Both quantities were known from careful experimental work, conducted decades before Maxwell assembled his equations. They were fundamental constants of electricity and magnetism, sitting in the equations as fixed numerical values. When Maxwell combined them in the way the wave equation required, dividing one into the other and taking a square root, the result was a speed, a single number with units of distance per time, determined entirely by the measured properties of electric and magnetic fields in empty space. Maxwell calculated it and found a value of approximately 300 million meters per second. He knew that number. Everyone working in natural philosophy at the time knew that number. It was the speed of light, measured independently by astronomers and experimentalists through observations of Jupiter's moons, through rotating mirror experiments, through methods that had nothing to do with electricity or magnetism. The speed at which light traveled through empty space had been determined to reasonable precision by the mid-19th century, and the value sitting in Maxwell's wave equation matched it with a precision that eliminated any possibility of coincidence. Maxwell noted this in his 1865 paper with a restraint that barely concealed the magnitude of what he had found. The speed of the wave predicted by his equations agreed so closely with the measured speed of light that it seemed impossible the two could be unrelated. An electromagnetic wave traveling at the speed of light was not a suggestive analogy or a loose resemblance. It was an identity. The wave his equations predicted and light itself were the same thing, and that conclusion restructured everything that physics thought it knew about what light actually was. Light had been studied for centuries before Maxwell wrote down his equations. Its behavior had been catalogued in extraordinary detail. It traveled in straight lines through uniform media. It bent when passing from one medium to another, following precise rules that allowed lenses and prisms to be designed with mathematical accuracy. It bounced off surfaces at predictable angles. It could be split into colors by a prism, recombined into white light, and made to produce interference patterns when passed through narrow slits. All of that behavior had been measured, described, and put to practical use in telescopes, microscopes, and optical instruments of every kind. What nobody had established was what light actually was. What was doing the traveling, the bending, the bouncing. What light was made of at the level of physical mechanism. The wave theory of light had been gaining ground through the early 19th century. Thomas Young's interference experiments had shown convincingly that light behaved as a wave, producing the same alternating bands of brightness and darkness that water waves produced when two sets of ripples crossed each other. Augustin Jean Fresnel had developed the mathematics of light as a wave, in detail sufficient to predict diffraction patterns with high precision. The wave character of light was well established experimentally. What the wave was waving in remained an open question. Waves in water involved water moving. Waves in air involved air pressure oscillating. Light waves seemed to travel through empty space where nothing material was present to oscillate, and that left the physical picture incomplete in a way that troubled careful thinkers. Maxwell's result closed that gap completely. The wave his equations predicted was not a mechanical wave requiring a medium to carry it. It was a wave in the electric and magnetic fields themselves, two physical entities that Maxwell's framework had already established as real, energetic, and capable of existing in empty space. The oscillating electric field and the oscillating magnetic field sustained each other through the mutual regeneration that the equations described, propagating forward at the speed the constants of electricity and magnetism fixed. No medium was required because the fields themselves were the medium, or more precisely because the wave required no medium at all, only the relationship between the two fields that Maxwell's equations encoded. Light was an electromagnetic wave. Every beam of sunlight crossing empty space, every candle flame illuminating a room, every color separated by a prism was a self-sustaining oscillation of electric and magnetic fields traveling together at 300 million meters per second. The bending of light at a glass surface was the response of those oscillating fields to the changed electrical properties of the glass. The reflection of light from a mirror was those fields bouncing off a conducting surface. The colors of the spectrum were electromagnetic waves of different frequencies, each frequency corresponding to a different rate of oscillation of the fields. Everything optics had measured and described for centuries was electromagnetic behavior, and the equations governing it were the same four equations governing the spark from a doorknob and the pull of a compass needle. Two forces that had seemed completely unrelated had turned out to be one, and that one force, when its fields were set oscillating freely in empty space, turned out to be the mechanism behind something that had been observed, studied, and marveled at since the beginning of human experience. The unification was not just a theoretical convenience, it was a discovery about the deep structure of nature, and its consequences extended immediately beyond visible light into a range of phenomena that no human eye had ever detected. Visible light occupies a narrow band within something much larger. Maxwell's equations placed no restriction on the frequency at which electromagnetic fields could oscillate. The wave solution they produced worked for any frequency at all. Slow oscillations, fast oscillations, oscillations so rapid they dwarfed anything visible light produced, oscillations so slow that a single cycle took longer than a heartbeat. Every frequency produced the same kind of wave, governed by the same equations, traveling at the same speed. Visible light was not a special case. It was the narrow slice of a continuous family that human eyes happened to be sensitive to. The implications were immediate and testable. If electromagnetic waves existed at frequencies below visible light, they should be producible in a laboratory using electrical equipment, since Maxwell's equations connected the oscillation of fields directly to the oscillation of charges in a wire. In 1887, Heinrich Hertz did exactly that. He built an apparatus that drove electrical charge back and forth in a wire at a high frequency, producing oscillating electric and magnetic fields that detached from the wire and propagated across his laboratory as a wave. He detected them at a distance using a loop of wire in which the arriving wave induced a small current. The wave travelled at the speed of light, reflected off walls, and behaved in every measurable respect exactly as Maxwell's equations predicted. Hertz had produced and detected radio waves, electromagnetic waves at frequencies far below visible light, using nothing but electrical equipment and the relationships Maxwell had written down 2 decades earlier. The full extent of the electromagnetic spectrum stretches across an enormous range of frequencies in both directions from visible light. Radio waves oscillate at the lowest frequencies, their wavelengths stretching from millimeters to kilometers, depending on the specific frequency. Microwaves sit above them, their wavelengths in the centimeter range, short enough to interact with water molecules in food and deposit energy there as heat. Infrared radiation sits above microwaves, felt as warmth on skin because its frequency matches the thermal oscillations of molecules near room temperature. Visible light occupies the narrow band above infrared, spanning the range from red through violet that the human eye evolved to detect. Ultraviolet radiation sits above visible light, carrying enough energy per oscillation to damage biological molecules, which is why prolonged exposure to sunlight burns skin. Above ultraviolet sit X-rays, whose short wavelengths allow them to pass through soft tissue while being absorbed by denser materials like bone, making them useful for imaging the body's interior. Above X-rays sit gamma rays, produced in nuclear processes, carrying the highest energies and the shortest wavelengths in the spectrum. Every one of these is the same phenomenon, a self-sustaining oscillation of electric and magnetic fields, propagating through empty space at 300 million meters per second, differing from every other only in the frequency of oscillation. The radio wave carrying a voice across a city, the microwave heating food in a kitchen, the X-ray imaging a broken bone, the gamma ray released by a decaying nucleus. All of them are solutions to the same four equations Maxwell assembled from the work of Faraday, Ampere, and Oersted. The physical mechanism is identical across the entire range. Only the number of oscillations per second changes, and with it the energy carried, and the way the wave interacts with matter it encounters. What the full spectrum reveals is that Maxwell's unification was not a description of three specific phenomena that happened to be related. It was a description of a single underlying structure that manifested across an unbounded range of physical situations, most of which had never been observed before the equations predicted they must exist. The spectrum is not a catalogue of different things. It is a single thing seen at different frequencies, and every part of it obeys the same rules that a compass needle and a current-carrying wire first hinted at in 1820. Begin with a doorknob. Charge builds up on your body as you walk across carpet, transfers to the metal the moment you get close enough, and releases as a sharp snap on your fingertip. That snap is an electrical event. Charge moving, fields collapsing, energy releasing in an instant. It feels like the most local and ordinary thing in the world. Something that happens to your finger in a room on an unremarkable afternoon. Nothing about it suggests any connection to the needle of a compass rotating in response to a wire, or to the light coming through the window, or to the radio wave carrying a signal invisibly through the wall. And yet all of those things are the same phenomenon, and the chain connecting them runs through one of the deepest structural discoveries in the history of physics. What Maxwell's framework established was not merely that electricity and magnetism were related. That much had been clear since Oersted's compass needle swung in 1820. What it established was that electricity and magnetism were two aspects of a single underlying entity, the electromagnetic field, and that the field, when disturbed, propagated that disturbance through empty space as a wave at a fixed and calculable speed. The unification was not a simplification imposed on two separate things for mathematical convenience. It was a discovery that two things thought to be separate were never separate at all. They were the same thing observed under different conditions, and the conditions that revealed their unity were nothing more exotic than motion and change. A charge sitting still produces an electric field. That same charge set into motion produces a magnetic field alongside the electric one. The magnetic field does not appear because something new has been added to the charge. It appears because the electric field of a moving charge, examined carefully, contains within its structure everything that a magnetic field is. The two fields are not independent entities that happen to influence each other. They are components of one field, and which component dominates depends entirely on the motion of the observer relative to the charge. This is not a classical insight. It points directly toward the special relativity that Einstein would formalize 40 years after Maxwell, finding that electricity and magnetism were unified, not just experimentally but geometrically, as two faces of a single four-dimensional field structure that the universe's geometry required. The consequences of the unification reached immediately into technology. Hertz demonstrated radio waves within 2 decades of Maxwell's equations. Within another decade, Marconi was transmitting signals across the Atlantic. The entire edifice of modern communication, radio, television, mobile phones, wireless internet, satellite navigation, rests on the electromagnetic wave that Maxwell found waiting inside his equations without looking for it. Every antenna ever built is a device for converting the oscillation of charge in a wire into an electromagnetic wave propagating through space, or for doing the reverse. Every one of those devices works because Maxwell's 4 equations correctly describe what happens when electric and magnetic fields change in time. But the deepest consequence is not technological, it is conceptual. Before Maxwell, physics contained forces. After Maxwell, physics contained fields, and the fields were real. Not mathematical tools for calculating forces between objects, but physical entities occupying space, carrying energy, propagating disturbances, existing independently of the charges and currents that produced them. The light crossing empty space between a star and your eye is not a signal passed between 2 objects across a void. It is a structure in the electromagnetic field, self-sustaining, carrying energy that left the star millions of years ago and has been traveling ever since with nothing supporting it but the relationship between 2 components of one field that the universe has always contained. Electricity and magnetism look completely unrelated at the start of this chain. A snap on a fingertip and a compass needle pointing north seem to belong to different departments of nature. What the chain revealed, layer by layer, is that the separateness was always an appearance produced by looking at one thing from too close a distance. Pull back far enough, let the mathematics speak, and what appears is a single field threading all of space, capable of storing energy, transmitting force, and when set, oscillating freely, filling the universe with light.